All right, in calculus 1, we defined the derivative like this. Do you guys remember the definition of the derivative?
Yes.
Okay, well, it's this limit. And if you wanted to approximate what is the derivative, you could just not take the limit and instead choose a really, really small value for h and evaluate f of x plus h minus f of x divided by h. So for example, if I want to approximate the derivative of the function 1 over x squared plus 1 at the point x equals 2, I can just calculate this, where the really, really small value of h that I've chosen is 1 divided by 1,000. So, what's the exact value? If my original function is 1 divided by x squared plus 1, then the derivative would be the derivative quotient rule, right? So it's minus 2x divided by x squared plus 1 squared. Yeah, I think that's it. And if I want the exact value of f prime of 2, that would be negative 4 over 2 squared plus 1, which is 5. 5 squared is 25. So that's my exact value. Or I could write 0.16. Is that right? Yeah. That's the exact value. What if I do it approximately? If I were to approximate this, I would need f of 2.001, so I'm going to type in 1 divided by 2.001 squared plus 1. .998. No, 0.1998. And I would need f of 2, which is 0.2. And then I would have to subtract these and divide by 0.001. So that number minus 0.2 divided by 0.001. So my approximation here, and I also rounded, I rounded to 4 sig fig, so there's going to be rounding error involved. But this is negative 0.1599. And it's pretty close. It's not bad. And the idea is if you choose a smaller number for h, this should get kind of closer to the actual derivative because the derivative is the limit as h approaches 0. That makes sense? Maybe you've even done this before sometime. Okay. So if I make h a positive number, then I would call this a right-sided derivative approximation because what I have of f of x on my number line, and then the other point is x plus some positive number, so it's on the right side. Alternatively, I could have an approximation where I'm still using the same thing, but if you replace the h with a negative h, then you'd end up with something like this. And this is what I would call a left-sided derivative approximation. And there's not one that's better than the other, right? I mean, who cares if you take a little step to the right and a little step to the left? As long as the step is about the same size, then I bet you're going to get about the same accuracy, right? because some functions are increasing, some functions are decreasing, some functions are concave up, some functions are concave down. So for functions in general, there's not like a better strategy, one or versus the other. One thing you might do, though, is you might say, I could do both the left side and the right side, and then average my result together. And that way I've got two opinions, and averaging them might give me a better approximation. And let's see what you would get. Because if I take the right side plus the left side and divide by 2 to get the average, I'm going to get f of x plus h minus f of x plus f of x minus f of x minus h divided by h divided by h divided by 2. And since I am adding fractions with the same denominator here in the numerator, that's fine, that goes away, and it's just an h. The f of x plus h stays, and the f of x minus h stays, but notice how the f of x's will cancel each other out, the negative and the positive. And so I get this. So sometimes this is called the central two-point derivative approximation. So it's kind of interesting. Notably, you don't care at all what the function value is at the point where you're taking the derivative. If I want the derivative at x, I don't even need f of x in this formula. I just need a point a little bit to the right and a point a little bit to the left. And also notice I'm dividing by 2h, so I'm dividing by kind of a larger step size than I was with the right side or the left side approximation. This is the central approximation then. And I have a question for you guys. What do you think is going to perform better? Central. Yeah, the central approximation is going to perform better, even though you're not considering the value of the function at the derivative, even though you're taking a step size that's twice as large, the central approximation is always going to be the best. You guys knew that right away, but when I taught AP Calculus, I did this, and all the students seemed to think that the right side or the left side would do better because you're taking a smaller step, in one direction versus another, but you'd be surprised. So what I did back in the day to prove to my Calculus 1 students that the central approximation really was better is we made an Excel spreadsheet. We compared all three. So we're going to have some value for h. We're going to get f of x plus h. We are going to get, and let's say the x is 2, right? And then we're also going to get f of 2 minus h in here. And that way we can calculate the left side approximation, the right side approximation, and the central. And so if h is 0.1, f of 2 plus h is, let me make a couple more columns here. I'll make a column for 2 plus h, a column for 2 minus h. So this is just going to be 2 minus that number. This is 2 plus that number. This is going to be 2 minus that number. My function that I'm dealing with right now is 1 divided by x squared plus 1. So for my left side approximation, what I'm going to do is take f of 2 minus f of 2 minus h divided by h. I think h was in A2. For my right side approximation, I'm going to take f of 2 plus h minus f of 2 and divide by h. For my central approximation, I'm going to take f of 2 plus h minus f of 2 minus h, and divide by 2 and divide by h. And we have the exact approximations right now, but what we might want is the percent relative error of the left side, the percent relative error of the right side, and the percent relative error of the central. And to get the percent relative error, I'm going to take the approximation minus the true value. What was the true value? 0.16. Negative 0.16. And divide by the true value. Make it a percent. And then, there we go. And then I don't just want 0 plus 0.1, but maybe 0.01, 0.001. Some of these. So let's fill in some of these and see what we get. Oh, something broke. Oh, that's because it'd be exactly 0.2. Okay. So let me give you a few more decimal places here. And I'll even just shrink these up. So you can see just this. As I'm making h smaller, all of these approximations are getting better in that the error is shrinking, right? Shrinking to 0. You start off with pretty bad error in your left side and right side approximations, but it gets better as you make h smaller. But the central approximation starts off pretty good and gets really, really good really fast. How many of you guys know how to use Microsoft Excel? Everybody?
A little bit. Not like that.
Okay. When I worked as an engineer, the only thing we did for like 8 hours a day was use Microsoft Excel. I mean, that's an exaggeration. Like we went to meetings and I was out in the field a lot and did a lot of inspections and worked with the operators. But a big part of the job was just using Excel. And I know that's not just engineering, but that's also business. That's like every job. So Microsoft Excel is a super important skill. And if you haven't already gotten really familiar with Excel, you should start getting familiar with Excel, right? Start working these problems out in Excel. But yeah, so this is just kind of a picture to show you that the relative formula, what I mean to say, the central derivative approximation, where you take a step to the left and a step to the right, you take the difference, that is a better derivative approximation than just a left-sided or right-sided, because it's unbiased, and you can think of it as averaging, you know, what's happening with the left side and the right side, kind of like taking votes. It's a better way to do things. Okay, the next thing I want to show you is this. As I make h approach 0, so h becomes smaller and smaller, I'm going to get a better and better approximation. But it only gets better up to some point. Because if you remember the very first day of this class, we talked about floating point data types, right? Like how do we actually represent numbers on a computer? There's going to be round off error. And so if we are going to divide by a small number, like if h is a really small number, dividing by a small number is going to amplify whatever error happens here when I subtract. And if h is, again, a small number, then this f of x plus h is going to be really close in value to this f of x. And when I subtract two numbers that are really close in value, I'm going to get a super duper duper tiny number. when I get a super duper tiny number, that subjects itself to a lot of round off error in a floating point data type. And so I'm already setting myself up for failure if I choose an h that's too small, because subtracting these numbers that are very similar is going to give me a lot of round off error. And when I take a lot of round off error and I divide it by a small number, it's going to blow it up into an even bigger round off error. So exercise 5, I really do want you to try this at home. I want you to illustrate the issue that we get with ever shrinking h if we make h too small by creating a log-log plot in Excel of the percent relative error versus the size of h when approximating f prime of 2. And that just means like, okay, I want to do what I just did here, but let's allow h to keep getting smaller. Okay? Do you see how in column A, my h value, my mesh size is getting smaller and smaller and smaller? And then what I'm going to do is I'm going to unhide these columns. Let's say we don't care about the left side and the right side. I'm just going to delete those and get rid of them. We'll just keep the central one since we know central is better anyways. I'm going to fill in all these formulas. And then you can kind of see already what's going to happen, right? I've got a rough approximation, and then a pretty good approximation, and then a really good approximation for a little while. And then look, oh no, the error creeps back in, doesn't it? Even though the h values are getting smaller, the error is growing. And the reason is because that round off error is creeping in. Okay, how do I make it not percent? There we go. All right, so the next thing I want to do is take the logarithm of h, and I can do this in Excel if I type in log equals log, and then I go select the h. And then I want the logarithm of the error. So I'm going to type in equals log, and then select the error. And it can't take the logarithm, why? Because I can't take a logarithm of a negative number. Oops. So what I should do is take the absolute error, just make that an absolute value by typing ABS in Excel. And now I can get all the logarithms. And now here's what I want. Insert, scatter plot, and with a line right here. What you're looking at as I go from left, well, as I go from right to left, I guess, because on the right side I have larger values of h, and on the left side I have smaller values of h, is the error. So as I'm going from large values of h to small values of h, my error is dropping, 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 dropping. That's great. That's exactly what I want. I want small error. There's a best point right here, a best selection for my h mesh size. And then if I continue to make h smaller, the round off error takes over and it starts making my approximation worse and worse and worse and worse and worse again. Until you can even see when you get to this point, the relative error is 100% because it thinks your derivative is 0. Why does it think the derivative is 0? Is because it's calculating exactly the same value for f of x plus h and f of x minus h. So there's a point where it totally fails, but even before it totally fails, it's still giving you more error. And so you want to actually choose the optimum value of h and not overshoot, not choose a too small value of h. There's actually a best h to choose. Choosing the best value of h is more of an art than a science. I think there probably is theory written about this, but not that we're going to discuss in class. What you should know about this is that how small you can make h depends on the data type. Are you using single precision? Are you using double precision? Are you using quadruple precision, IEEE floating point data type? The more precise the data type, the smaller you can make h safely. It depends on the function, because if your function has a larger derivative there, it's going to be more steep, and you can make h smaller before those function values get too close to each other. And so you can get a smaller h if your function has a larger derivative, and if your function has a very shallow derivative, then you need a very large value of h. So it depends on the function too, and likewise it depends on the point where you're trying to find the derivative. The best value of h for approximating the derivative depends on the value of the derivative that you're trying to find. So if we've chosen a value of h based on experience that we think is going to perform well, you know, we're not making it too small, so we're not drifting into the round off error regime. If we choose that value of h and we can't make it any smaller, just don't want to risk it, how could we still increase the accuracy of our derivative approximation? And the answer is we use a differential quadrature. So it's like the integral quadratures we've been discussing so far. You're still going to take a linear combination of the function values, which means you're going to add up a bunch of weights times the function evaluated at nodes, just like we did with integral quadrature, but this time the point is to approximate a derivative. So you get to choose the k+1 node locations. And then we're going to calculate what weights are required to find the derivative of the degree k interpolating polynomial exactly. Same kind of setup. So if I take the Lagrange interpolating polynomial, which is just the function values at the nodes times the Lagrange basis polynomials all added up. And what I'm trying to find is not the integral, but the derivative of this Lagrange interpolating polynomial evaluated at some point p where I want to know the derivative. Then, okay, take the derivative of this, and the only function that has an x is the Lagrange basis polynomial, so we take the derivative of those, and then we plug in x equals p. And this looks like our quadrature, right? This looks similar, where the weights would then be determined by the Lagrange basis polynomial, or I should say the derivative of the Lagrange basis polynomial evaluated at p. So that's exactly how we're going to calculate those weights. So remember, this is what the Lagrange basis polynomial looks like. And when I take the derivative of the Lagrange basis polynomial, you're going to use the derivative product rule. So the derivative product rule says you take the derivative of each factor, right? And then you end up adding up, like, let me give you a smaller example. If I've got a product f times g, and I want to take the derivative, that would be f prime g plus fg prime. What if I have the product fgh? That's going to be f prime gh plus fg prime h plus fgh prime. In other words, after using the derivative product rule, you're going to have a number of terms that corresponds to the number of factors. And in those terms, you just take the derivative of one factor at a time. That's how my derivative product rule works. And so when I've got this big capital pi product, and I don't know how many factors I have, what I do know is that when I take the derivative of one of these guys, the derivative is going to be 1 divided by xj minus xi. And then I'm going to multiply that times the rest of the factors unchanged. And then we're going to add up all those terms. So that's where the sigma comes from. And You'll also notice that it doesn't really matter whether I'm adding up a bunch of terms that look like this leading coefficient times the product, or if I take the product out, like I'm factoring, right? Basically, right now I'm factoring out this big capital Pi product in this step, but it's the same thing. So what if we choose an odd number of nodes? And I'm going to like choosing an odd number of nodes. It's the only thing we're going to do for derivatives. We're not going to choose an even number of nodes because we're going to only do in this class central derivative approximations. We're like, here's the point where I want to take my derivative. And then I can either call this a 3-node approximation if I calculate the value of the function here at the orange points, or I can do a 5-node approximation, or I can do a 7-node approximation. But if we are restricting ourselves just to central derivative approximations, and that's what we're going to do, then you're going to have the same number on the right side and the same number on the left side. And we canonically count the middle point as being a node, even though we don't really care about the value of the function there. We're still going to pretend it's a node, so we would still say this is an odd number. We'd still say there's 7 nodes. So that's what I mean when I say, suppose we choose an odd number of nodes, and P is the middle of these, and that means it's kind of central and symmetric. We are going to try to calculate what these weights should be, and it's going to be easier if we shift everything and translate and scale it up so that the first node is going to occur at the integer 0, and the last node is going to occur at the integer k, and all of the nodes that are evenly spaced in between are going to happen at those positive integers between 0 and k. And then the middle node is going to be p equals k over 2. When we're done calculating the weights in the special case, the special circumstance, I'll show you how to translate this into the general case whenever we don't want to have a 1 mesh size. So anyways, replacing the nodes with those integers between 0 and k, this is what it looks like. And then suppose we consider the case whenever I set the Lagrange basis polynomial equal to the midpoint where I'm calculating my derivative, then this is what it looks like. And this part, the sum, is going to turn out to be 0. It's going to turn out to be 0 because there's going to be a bunch of positives where m is less than p being the midpoint. And then there's also going to be a bunch of negatives where m is greater than p. And for every positive value, there's a corresponding negative value with the same but opposite value. So they're all going to cancel each other out. In the case where j is equal to p, the terms of this sum all cancel each other. Those terms cancel in pairs. So that means the weight for the middle node is 0. And that means just like with the central derivative approximation, we don't care what the value of the function is where we are trying to take the derivative. If it's a central derivative approximation, you just end up getting a weight of 0 every time. Okay, well, now suppose that I'm looking for a different weight, a weight that's not at the central location where I'm trying to take the derivative. Well then, I end up with a situation this is a way of taking the same thing and expanding it out so that I'm taking away the m equals p term in this sum, and instead I'm making m equal to p over here. So I'm just taking one of the terms away from the sum and I'm expanding it out here on the right so that you can see it a little better. Then once again, this is going to be 0. Actually, this product is going to be 0, the one I'm pointing at right now, is going to be 0 because there will be a point, there will be a factor in here where I is equal to p. And so that's the reason why this is a 0. The other part of this, where this product gets turned into this product, you just gotta sit and think about this. I don't know. Make yourself a cup of tea and sit in your armchair tonight and like think about this deeply. But it really does work if you try to read into the math a little bit. Maybe make yourself a little example problem to work through. But gosh, I don't know. It's because these i's are moving, right? The i's are moving from 0 to k, and in the numerator you don't have I equal to p, but you have I equal to everything else, and so you're going to end up with this p factorial because p is half the distance from 0 to k, and so the negatives and the positives both give you factors, so there's 2 of them, that's why it's squared, and the factorial because it's rising. I don't know. Sit and think about it. That's my recommendation. And then when you simplify this up, you get your weight formula. Now, that's the weight formula if you were to have a mesh spacing of 1. When I say mesh size, I mean the mesh size of evenly spaced nodes is going to refer to the distance between 2 adjacent nodes. And we assume the mesh size was 1. If you want to generalize this to any mesh size, because we don't want to have a mesh size of 1, we want to have a relatively small mesh size, all you got to do is divide by h. So here is the formula for evenly spaced nodes, uniform spacing, a central derivative approximation with k plus 1 nodes. That's the deal. That's the one you want to know to calculate the weights in your differential quadrature. So what we're going to do is we're going to calculate the percent relative error of the derivative approximations of f prime of 2, same function. And we are going to use h equals 0.001, and we're not going to change that mesh size. We're just going to stick to it. Because it's relatively small, but it's not too small where we're going to run into round-off errors. And then what we're going to do instead of making h smaller is we are going to choose larger and larger numbers of nodes for the differential quadrature. We're going to use n equals 3, n equals 5, n equals 7, and n equals 9. And if you choose n equals 3, this should be the same as the central 2-point derivative approximation that we talked about earlier, right? Because n equals 3, we don't count we count the middle point where we take the derivative, even though we don't really use it. So that would be the n equals 3. And then we'll do this for 3, 5, 7, and 9. That's the goal. And so let's keep this weight formula up. And I'm going to pick out a new page of Excel. And then we're going to need some nodes. And if I want an approximation with 9 nodes, I think that was the biggest one I need, is 9. Then I'm going to have a -4, -3, -2, -1, 0, 1, 2, 3, 4. And the nodes are going to be 2 plus my mesh spacing times j. And for each of these nodes, I'm going to have my function evaluated at the node, and that is going to be 1 divided by x squared plus 1. And then I need the weight. And for the weight, I'm going to need my weights formula. The weights formula is -1 raised to the power of p minus j. And remember, p is k divided by 2, so this is going to be, I don't know, I'm going to make a k over here. K is 9, so that p is 9 divided by 2. No, sorry. K plus 1 is 9. That's my number of nodes. So that means k is 8, and then p is 4. So I need -1 raised to the power p minus j but I did my j's wrong. That's not the same j as before. Sorry. What I really need is j 1, 2, 3, 4, 5, 6, 7, 8. And then these nodes would then be that times j minus p. Okay, now I've got the right nodes. I've got the right j's to use in my weight rule. I need to lock this E6 into place, so I'm going to hit F4 so that doesn't move, times p factorial. So in Excel you type in fact for factorial, and then you square that, divide by h, so I'm dividing by 0.001, divide by j minus p, so that's a2 minus E6, and then divide by j factorial, and then divide by the factorial of k minus j. So that's E4 minus A2. Cool, that's my weight. Okay, now that I have my weights, and you'll notice it's not going to calculate the middle weight because, again, the middle weight should be 0. We don't care about the middle. And then we can add these up, or I should say multiply first and then add. Excel has a fancy function called sum product. So if you type in equals sum product, it's going to multiply and add at the same time, so it's perfect for quadratures. You can multiply the function value times the weights, like that. Just select the 2 ranges, and then hit enter. And so that's my approximation. That's my quadrature. So that's like scary good, because the true value was 0.16. And the percent relative error would be the absolute value of, the approximation minus the true value divided by the true value. So there's my percent relative error. But this was for k equals 9. If I want this to be k plus 1 equals 9. If I want this to be k plus 1 equals 7, oops. The center moved to right here. Is that even better? It's kind of weird. This time it has a better relative error. Okay, let's try k plus 1 equals 5. And then k plus 1 equals 3. And here it's, so this is 9 nodes, 7 nodes, 5 nodes, and 3 nodes. Let me line up these relative errors. For 3, 5, 7, 9. Huh. Yeah, that's the weirdest thing. I would have thought that 9 nodes would do the best, wouldn't you? It's like pretty close, but I guess 7 nodes perform the best. A little bit strange. Okay, sorry if I was going a little bit too fast. I just didn't want to waste all my time on this example. I don't want to waste all of our lecture time, so I was trying to do that as quickly as possible. But yeah, I understand if you're not familiar with Excel, that could be a little intimidating. But at least try that. At least try to plug in the weights formula in Excel and see if you get the right answer. I'll make that one of the test questions. And obviously you don't have Excel on a test, but I'll see if you can just calculate the weights correctly using this calculator, right? I'm not going to make you like invent the weights formula from scratch on a test, but I think you should be able to like try it like one time, kind of like on the last test. I made you do a Crenshaw-Curtis quadrature just to make sure you understand how the calculation is done. Okay, the degree of exactness for a differential quadrature with k plus 1 nodes is k. By construction, we just set it up that way. We just made it so that if you take the interpolated polynomial of degree k, it will get the derivative of that interpolated polynomial of degree k exactly. And then the last critical piece here is that if you have a polynomial of degree k and you interpolate that polynomial with a polynomial of degree k, you get identically the same polynomial, right? There's only one interpolating polynomial of degree k. All right, the next one is a proof that's a little bit more involved. We say the differential quadrature with an odd number k plus 1 of evenly spaced nodes placed symmetrically about the point of evaluation will have an absolute error asymptotically proportional to h to the power k. So this should feel like deja vu. It should feel a little bit familiar to what we did with integral quadratures back in our Newton-Cotes quadrature lecture. But there's a proof here. You label the nodes. So where I have j equals 0, that's going to correspond to p. And p is the place where I'm trying to evaluate this derivative. Okay, p is in the middle. And the other nodes are going to have j values that are negative down to negative m, and j values that are positive going up to positive m. But j is all of the integers between negative m and positive m. And so this is a formula that I can use to find the nodes. and the mesh size, the distance between nodes, is h. So now let capital L be the interpolating polynomial of degree k of the function through these nodes. And back in lecture 3.3, when we very first started talking about interpolating polynomials, we came up with this formula that gave you the error of just the interpolating polynomial at the point x. And we're going to use this, right, where it says omega of x. It just means this product, where you take x minus each of the nodes and you multiply all those factors together. Since we want the derivative of this interpolating polynomial to approximate the derivative of my function, we're going to take the derivative of both sides of this equation, and then we're going to evaluate them at p. But this k plus 1th derivative of f at this Greek letter c, that's not a function of h. It's just a constant. K plus 1 factorial, that's not a function of h. It's just a constant. So what we really care about is this omega prime of p factor. When we are looking at this omega prime of p factor, we're going to make a little substitution. We're going to replace the x variable with this. We're going to set u equal to x minus p over h. That means the derivative of u with respect to x is 1 over h. So a little u sub. And that means we get to define a new polynomial, lowercase q. And what's nice about lowercase q is that the omega product that we were pointing to in the error formula is just going to be equal to h raised to the power k plus 1 times q of t. And the reason that is, you can see on this line, the big expanded line that has a bunch of equal signs. You can kind of follow this a little bit. Going from this xj, this is a node, to here, that is a formula for the nodes that we set out at the very beginning right here, replacing it with p plus jh. In this next step, I'm distributing the minus sign. So it's x minus p minus jh. So we're distributing the minus sign. And Kevin, what's happening in this orange step?
So replacing x minus p with minus m.
What we're doing is we are replacing... Oh, shoot. Oh, that's ugly. I just realized there's a big typo here. This T should be a U. It's my bad. I'm glad I caught this. All right, I bet this makes more sense, right? What we're doing is that substitution. We're saying that U is equal to x minus p divided by h. And so what we're doing in this orange step is we are factoring out all of the h's. In this product, there's k plus 1 factors. So if I divide all of those k plus 1 factors by h, I'm going to get h to the power k plus 1. And then whenever I divide x minus p divided by h, I'm going to get the u. And when I divide jh divided by h, I get a j. And now that's what I want. Glad I stopped to point that out in more detail so now that I can catch all my dumb typos. I don't know why I mentally switched from using a U to a T, but the symbols aren't important, but being consistent with the symbols you use is important. So I'm going to need to go back and fix that in my lecture notes. All right, so this is my omega. It's omega of x is equal to h to the power k plus 1 q of u. And when I want to take the derivative of omega and get omega prime of x, this is just the derivative chain rule. H to the power k plus 1 remains the same, then I take q prime of u, and then the derivative chain rule says I also have to multiply times the derivative of u with respect to x. So I multiply by the derivative of u with respect to x, and I get, well, what is the derivative of u with respect to x? This derivative of u with respect to x is 1 over h. And that's why the power of h goes down from being h to the k plus 1 to just h to the k. It's because of that derivative chain rule. So we find that omega prime at p is the same thing as h to the power k times q prime of 0. Again, because if I plug in x equals p, then u is equal to 0. And instead of having q of u, or q prime of u, we're going to have q prime of 0 when I plug in x equals p. X equals p implies u equals 0. So you can already tell where the h to the power k comes in, right? Just to recap here. We've got this error formula, and that was from a previous lecture, but when we want to take the derivative, now my error in the derivative is like this, and it's proportional to omega prime of p. And we just showed now that omega prime of p is proportional to h to the power k, and that's what we're trying to show. The last thing you might be interested in, though, is like, what is that q prime of 0? At this stage, all that's left to find is q prime of 0. And again, I use t's. We'll just suffer through the t's for right now. Q of t is this product, right? And since the j's are placed symmetrically about 0, they're going from all the integers negative m to positive m, then I could make this product go from j equals 1 to m and just include t minus j for the positives and t plus j for all those negative values of j. And it's the same product. I also put a little t factor for when j is equal to 0, right? T minus 0 is just that t factor out front. And then we can multiply this, and if you FOIL t minus j times t plus j is t squared minus j squared. And taking the derivative of q with respect to t and then plugging in t equals 0 looks like this. Imagine the derivative power rule again. Sorry, product rule. Imagine taking the derivative product rule here again, but if I take the derivative of t and leave all of the other factors alone, I get this. And then I plug in t equals 0. If I instead don't take the derivative of t, and I take the derivative of one of the other factors as part of the derivative product rule, then the t remains completely intact. And whenever I plug in t equals 0, those terms go away, and we don't have to worry about them because they get multiplied by a 0. So then I've got this product of all these 0 squareds minus j squareds. That's a product of a bunch of negative j squareds So the product of a bunch of negatives becomes this -1 to the power m. And the product of a bunch of j squareds becomes the product of a bunch of j's squared. And that's a factorial. That's m factorial, because m is the upper bound here. This is notably not a function of h. And it's also not 0. And if it's not a function of h and it's not 0, then it doesn't mess up the whole proportionality thing. So to recap, we had this error formula that we got from Lagrange, and then we had this made-up definition of omega prime of p, and it's proportional to h to the power k. This q prime of 0 turns out to not be 0, so it doesn't mess up everything, and it's also not a function of h, so we don't have anything else to worry about. And that means my error is proportional to h to the power k. And that's exactly what we're trying to find, is that the absolute error should be asymptotically proportional to h to the power k. So remember the big O notation? Big O means asymptotically proportional to. Since h is going to be a small number, you want it to be h to a big power, and that represents more accuracy. In the context of integral quadrature, so before today, we learned that evenly spaced nodes were not the best way to approximate an integral. So let me ask you, in derivative quadrature, are there any orthogonal tricks that we can use, like in Gauss-Legendre quadrature? No. Yeah. Orthogonality, like the orthogonal polynomials thing, the Legendre polynomials, that really helped us a lot in getting like a huge boost to the degree of exactness when we were doing integral quadrature. But with derivatives, there is no trick. There's no reason that you should place the nodes here or there to boost degree of exactness. There's not any way to do it. Okay? In the context of integral quadrature, we learned that evenly spaced nodes were not the best way to approximate the integral. You might ask, in derivative quadrature, should we be using Chebyshev nodes because we want to minimize the effect of Runge's phenomenon, like we did with Clinchok-Curtis-Fayer quadrature? No. It turns out it doesn't matter. We don't care about Runge's phenomenon. I'll tell you why. When you look at these pictures, I've got evenly spaced nodes on the left and Chebyshev nodes of the first kind on the right. You remember Chebyshev nodes of the first kind are the very, very best. It's the optimal way to minimize Runge's phenomenon. But Chebyshev nodes are doing better near the endpoints. Evenly spaced is doing worse near the endpoints. But evenly spaced is actually doing better at approximating the function near the middle. And Chebyshev nodes do a worse job, just slightly, but do a slightly worse job at approximating the function near the middle. Here's the same thing with n equals 7, and again, the endpoints are getting worse for evenly spaced. But notice that if I only cared about what's happening in the middle, evenly spaced nodes are doing a better job of capturing what's happening in the middle versus Chebyshev. And Chebyshev's not doing a terrible job, it's just not doing as good. Likewise, n equals 9, n equals 11. And with integral approximation, I had to care about what's happening over the entire length of the interval. I had to care about these big areas that were going to make an issue for me when I try to integrate. But if I only care about the derivative at this point, if this can be as bad as it wants to, I just want this part to be as accurate as possible, right? And so for that reason, evenly spaced nodes are actually a better deal than Chebyshev nodes. When approximating an integral, we must care about the accuracy along the entire interval. When approximating a derivative, we only care about a close fit near the middle. So what you would like to do for calculating a derivative is, say I want the derivative here, I just need to make sure that I give it appropriate space, we'll call it h, and put down 2 points. And that's the best we can do for 3 nodes. And if I want 5 nodes, I'm going to give it the same amount of space and put down 2 more nodes. If I were trying to make an uneven node spacing, well, I could move these nodes in and make them closer to the middle, except we already said h is as small as I want to be without risking any kind of round-off error. So I don't want to bring them in. The other way I could get an uneven node spacing is by pushing them out a little bit. But pushing them out a little bit means I'm going to be farther away from the center, and so my interpolating polynomial is not going to capture what's happening at the center as well. So it turns out the very best way to do derivative approximations is with evenly spaced nodes. Yeah. And I think this is, I mean, I personally think that this is pretty cool. I think it's cool that even though derivatives are like a, I don't know, even though derivatives are a local phenomenon, you only really care about what's happening at the function at that point. It's not like a global phenomenon like an integral where you really care about what the function is doing over an interval. You can still get a better approximation of a derivative by taking more nodes in the surrounding space, which I think is just kind of crazy. There's a few reasons why I like numerical analysis. I think the story of Gauss-Legendre quadrature is neat. How you can get a degree of exactness that's far beyond the number of nodes you place down using this orthogonal trick. I think that's like genius. That's like really awe-inspiring. And then the other thing is like derivative quadratures. Just the fact that knowing values of your function farther away from the derivative point helps you come up with a better approximation of your derivatives is kind of crazy. Okay, questions?